Imagine a power source that isn't just renewable, but truly living, a device that doesn't just store energy, but literally grows, sustains itself, and creates power directly from the subtle, unseen processes of nature. Today, we're embarking on a journey into a concept that is radically redefining what a battery can be, pushing the boundaries of engineering and biology into, well, a really exciting new frontier. We're going to unpack the extraordinary, almost visionary concept behind something called the natural living battery, or NLB. Our mission for this deep dive is to shortcut you to a comprehensive understanding of this truly radical new energy platform. We'll explore precisely how it leverages ancient earth chemistry, microscopic life, and intricate fungal networks to generate power, why it could be an absolute game changer in our quest for sustainable energy, and what its emergence might mean for our future relationship with technology and the very environment around us.
And we have some absolutely fascinating source material that serves as our blueprint for this exploration. It's really quite detailed. Our primary guide is a research proposal titled Toward a Natural Living Battery, Integrating Geochemical, Microbial, and Fungal Systems for Sustainable Bioelectrochemical Energy Harvesting. And this isn't just some speculative paper. It's a meticulously thought out plan. Alongside that, we have an annotated design framework that truly breaks down the nuts and bolts, laying out the precise engineering and biological components envisioned for this system. These documents aren't theoretical musings, they are, in essence, detailed blueprints for a tangible future, outlining a very specific and frankly ambitious path to creating this groundbreaking technology.
The phrase natural living battery itself is almost jarring, isn't it? It really catches you. It sounds like something plucked from the pages of a deep future science fiction novel, or maybe a segment from a particularly forward-thinking nature documentary. So let's strip it down. For someone hearing this for the first time, what's the elevator pitch for what this natural living battery truly is? What are we actually talking about when we say living power?
Right. At its fundamental core, the NLB is a novel and critically a fully biodegradable bioelectrochemical device. Think of it less as a traditional battery and more as a living, breathing, sort of self-sustaining power generator. Its central purpose is to produce sustainable, low-voltage power by ingeniously fusing three distinct yet naturally occurring biological and geochemical systems. First, you have geochemical hydrogen generation. This is a primary chemical reaction drawing inspiration from the earliest days of Earth, literally leveraging primal geological processes. Second, it harnesses hydrogenotrophic microbial metabolism. That means it utilizes tiny microscopic organisms that literally feed on the hydrogen gas produced in that first stage. And third, it integrates electroactive fungal networks, making use of the remarkable conductive and growth properties of fungi to create living, regenerating electrical pathways. It's quite the combination.
Wow.
So the ultimate goal here isn't just another battery to toss away. It's a truly self-renewing energy platform. Its primary applications are envisioned for low-power needs, things like microelectronics, maybe remote sensing devices far from traditional grids, and even as interactive educational tools.
Educational tools, like you can see it
Yeah,
working.
exactly. Allowing people to literally observe and interact with a living system generating electricity. It represents a radical rethinking of what constitutes a power source in what researchers term a post-carbon age, moving away from resource-intensive extractive processes by using layered organic and mineral materials designed to exist in harmony with the natural cycles. The aha moment here, I think, is that it's not just using biology, it's becoming a biological system in itself.
That distinction feels crucial. It's not a static, inert container of chemicals like, a typical AA battery. You're emphasizing that it's a living system. What does that living aspect truly entail according to that annotated design framework you mentioned? How does it actually live and breathe, so to speak, in a way that's different from any energy tech we have now?
That's precisely the revolutionary element, yes. The annotated design framework really drives home that the NLB is a hybrid bioelectrochemical system. It's not only layered and modular in its construction, meaning, it can be scaled up or down depending on the need, but it's also designed with intrinsic principles of scalability, biodegradability, and most critically, self-renewal.
Self-renewal, so it fixes itself.
To an extent, yes. This is not a use and dispose device. Instead, it leverages inherent biological growth and natural regenerative processes to continuously maintain or even repair and regenerate its own components. Think about how a forest replenishes itself after a disturbance, or how a plant grows new leaves. The NLB is designed to mimic these inherent biological processes for its own energy generation and structural integrity over time.
Okay, that's fascinating.
This means the biological components within the battery, the microbes, and the fungi, they aren't merely static actors. They are active participants in its ongoing function and resilience. They grow, they metabolize, they interact, collectively ensuring the system's longevity and efficiency. This active, continuous biological involvement is fundamentally different from any conventional battery we know today, where components just degrade irreversibly and need full replacement.
Right.
The living aspect means it has the potential for a vastly extended operational lifespan without human intervention or external material input, beyond just needing the right basic environmental conditions. It's a truly symbiotic relationship between technology and nature.
Okay, but we do already have various forms of bioenergy today, right? Things like microbial fuel cells, MFCs, they've been around for quite a while. I remember reading about them years ago. What are the current limitations of these existing technologies that this natural living battery is trying to leapfrog? What are the specific hurdles it's designed to overcome?
That's an excellent and critical question, yeah, because the NLB isn't operating in a vacuum. It's definitely building on and aiming to move beyond prior innovations. While existing microbial fuel cells and maybe enzymatic biobatteries have indeed made significant strides in generating low-power bioenergy, they often encounter substantial practical limitations. For instance, many MFCs suffer from low power density. They produce very little power for their size, which makes them impractical for a lot of applications.
Right, you'd need a huge one for anything useful.
Pretty much. They can also be quite expensive to manufacture at scale, often needing complex electrode materials or very precise controlled environments. That limits widespread adoption. Another common issue is their relatively short operational lifespan and a lack of true self-sufficiency. They might need specific organic inputs food for the microbes that depletes over time, or they can be susceptible to contamination, leading to performance degradation.
Okay.
Furthermore, their ecological integration can be a challenge. They aren't always designed for full biodegradability, sometimes still leaving behind components that need special disposal. And they often lack a robust, continuous fuel supply that can operate autonomously in varied natural settings. These are the kinds of limitations the NLB directly tries to address.
So how does the NLB expand on the breakthroughs that have been made? You mentioned specific research.
Yes, it builds quite directly on recent work. The proposal mentions research by Reyes and colleagues in 2024 on cellulose-based fungal batteries. That was groundbreaking because it showed how certain electroactive fungi could be integrated into sustainable cellulose-based materials to generate energy. It sort of established the potential of fungi as living electrode materials.
Ah, okay, so that's the fungal link.
Exactly. And similarly, studies on hydrogenotrophic microbial electron transport papers published in Catalyst and FMICB recently, they meticulously worked out the precise biochemical mechanisms. They showed how certain microbes can breathe out electrons directly onto conductive surfaces, and the best ways to harvest those electrons from hydrogen metabolism. These studies provide the biochemical blueprint for the NLB's microbial layer.
Okay, so it's integrating these recent advances, but what's the really new part?
The truly radical leap, I'd say, is its unique integration of prebiotic geochemistry. This refers to the chemical reactions, the kind that happened on early Earth before life really got complex, as an in situ, meaning on-site and self-contained hydrogen generator.
So it makes its own fuel right there inside the battery.
Precisely. This passive, continuous hydrogen supply from a simple, naturally occurring reaction is a potential game changer. It means the fuel source is self-generated. It doesn't rely on external, perishable organic stuff or complex plumbing. And then it uses the fungal mycelium not just as a simple structural element, like some earlier concepts, but as a truly conductive, regenerative scaffold.
The living wires idea again.
Yes. The fungi aren't just holding things together, they are literally the living, growing wires and active parts of the power generation process. This full system-level integration of all three elements, the geochemistry, the microbes, and the fungi, in one cohesive, self-renewing, biodegradable device, well, that just hasn't been realized before. It's a truly novel, holistic approach.
That really does sound like it could open up an entirely new realm of possibilities, especially with that focus on sustainability and running by itself. Beyond the theory, what specific real-world applications are the researchers actually envisioning for this kind of sustainable modular power system? Where might we actually see these things deployed?
Well, the proposal highlights its immense promise for off-grid applications. That's a huge area with lots of unmet energy needs. Imagine remote environmental sensors, maybe deep in a forest or embedded in a field or even at the bottom of a lake, that don't need anyone to go change their batteries, ever.
Wow.
They could monitor soil health, water quality, wildlife movements for years, maybe decades, powered autonomously by the very environment they're studying.
That gets rid of a huge logistical headache. And the waste, too.
Exactly. It also holds significant potential for emergency power in rural communities or disaster areas cut off from the grid. Now, it wouldn't power an entire house, obviously, but it could provide crucial power for basic microelectronics, low-power communication devices, maybe basic lighting, medical sensors, charging small essential things like phones.
Right, where traditional power is just impossible or gone.
Precisely.
Yeah.
Because it's designed to draw power from basic ambient natural processes, it's inherently suited for those environments. And beyond utility, it's seen as ideal for those educational deployments we touched on.
Yeah, the classroom battery.
Yeah. Imagine students literally observing and interacting with a living system generating electricity. It could really transform how we teach energy, biology, chemistry, making abstract concepts tangible. And crucially, it's envisioned for ecological sensor networks. Think about sensitive habitats where traditional batteries, at the end of their life, pose a significant waste problem.
They leak nasty stuff.
They do. The NLB's intrinsic biodegradability means it could just decompose back into the environment, maybe even enriching the soil rather than polluting it, leaving no harmful trace. That's very appealing for ecological research.
This raises a really important question for our modern world, doesn't it? We're increasingly worried about climate change, resource depletion, the mountains of e-waste we generate. How does this NLB truly embody the ideal of a post-carbon age power source? What makes it so profoundly environmentally aligned, beyond just being, green?
Its biodegradability is absolutely paramount here. It directly addresses one of the biggest challenges of our tech today: electronic waste. Unlike conventional batteries, which, as you said, often contain heavy metals, lead, cadmium, mercury, plus toxic chemicals and rare earth minerals.
Which are awful to mine and often end up in landfill anyway.
Exactly. They reach toxins, the recycling's complex and energy intensive. The components of the NLB, however, are designed to break down naturally and safely. They return to the earth as harmless organic matter, ideally, without leaving that toxic footprint. It's a fundamental shift from our current linear take-make-dispose model. It aims to close the loop.
Okay, that's huge.
And furthermore, the self-renewing aspect dramatically reduces the demand for constant replacement and the continuous extraction of new resources. Think about the massive mining needed for lithium, cobalt, nickel. These processes are energy-intensive, can destroy habitats, pollute water, emit lots of carbon, plus all the complex geopolitical issues around supply chains.
Yeah, it's a messy business.
It is. By drawing power from basic, naturally occurring reactions and living systems, essentially, ambient biology and fundamental geochemistry, the NLB bypasses the need for fossil fuels for its operation and aims to minimize that high-impact mining. It's really about designing technology that works with nature's cycles and abundance rather than just imposing external resource-intensive demands. It embodies a circular economy approach. Waste minimized, resources regenerated. It's designed to be inherently regenerative, not just less bad.
All right, now that we understand the what and the why, this is where it gets really fascinating for me. Let's get into the intricate mechanics. How do these incredibly diverse natural and living systems, geochemistry, microbes, fungi, how do they actually come together in a coordinated way to generate electricity? It sounds like a biological orchestra almost.
Yeah.
How do they pull it off?
It is indeed a remarkably complex symphony, you could say, but one that's elegantly structured in distinct layers, like that biological sandwich idea. The methodology in the research proposal describes this multi-layer design, where each layer has a very specific interconnected function. When all these layers work in concert, precisely calibrated and interacting, that's when you get the stable electrical output needed for microelectronics. It's a real testament to biomimicry, taking cues from nature's own efficient designs.
Okay, let's start at the very bottom of this biological sandwich, the foundation. What exactly is this geochemical core, and how does it kick off the whole process? You called it an engine earlier.
That's a very fitting analogy, yeah.
Yeah.
This is truly the foundational layer, the bottom of the stack, and it acts as the passive hydrogen engine for the whole system. Its main job is the continuous passive generation of hydrogen gas, HOs. And it does this through a remarkably simple yet powerful chemical reaction. You just mix powdered iron sulfide, FeS, a very common mineral, with a weak acid.
Like vinegar.
Exactly. The research suggests easily accessible weak organic acids, like acetic acid, vinegar, or citric acid from lemons. When these two components react in the presence of water, they naturally and continuously produce hydrogen gas. No need for external energy input like heat or electricity. It's a self-sustaining chemical process.
Okay. And why hydrogen? What's the point of making that?
The H is absolutely crucial. It supplies the necessary reducing power. Think of that as the fundamental fuel or the electron donor for the microbes in the layer directly above it. Hydrogen readily gives up electrons, chemically speaking, and these electrons are what the microbes will essentially eat to generate their own energy, which then gets channeled into our electrical circuit.
Got it. Fuel for the next stage.
Precisely. The design framework specifically notes this system is inspired by those prebiotic vent systems, deep in the oceans of early Earth. Those were places where similar simple geochemical reactions happen, providing the initial energy and chemical building blocks for the very first life forms.
So it's tapping into really ancient chemistry.
It is. It means the NLB's geochemical core is designed to work efficiently and consistently in low-energy natural environments without needing constant tweaking or external energy. It embodies that self-sustaining principle. The beauty is in its simplicity and reliance on Earth's own chemistry.
So this geochemical core passively makes a continuous supply of hydrogen fuel. Makes perfect sense as the engine. What happens in the very next layer with the microbes? How do they turn that hydrogen into something useful, electrically speaking? Are they like tiny biological power plants?
They absolutely are. Miniature biological power plants is a great way to put it. This microbial electrode layer is where the HERO gas from the core gets actively consumed. This layer hosts specific types of microbes, mainly things like Acetobacterium woodi or Methanobacterium species. These are what we call hydrogenotrophic microbes. It literally means they are organisms that thrive by metabolizing or eating hydrogen gas as their main energy source, and they're anaerobic, meaning they don't need oxygen, which suits the internal environment of the NLB perfectly.
Okay, so they eat the hydrogen, then what?
As they metabolize this hydrogen, they do something really fascinating called extracellular electron transfer, or EET. Think of it like this. Instead of using oxygen to breathe and make energy internally, like we do, these specialized microbes have evolved a way to exhale their electrons directly outside their cells onto a conductive surface.
Wow, really?
Yeah, they effectively turn themselves into microscopic living power sources directly connected to our circuit. This direct electron transfer from their cellular processes to an embedded anode in their layer generates the electrical current. The electron flow from their collective biofilm, that's the community of microbes living together on the surface, feeds right into the larger electrical circuit of the battery.
How do you make sure that happens efficiently?
Well, the microbes are housed on a porous carbon felt. This gives them a large surface area to colonize and grow their biofilms. And the research proposes testing various nanomaterials, like conductive nanoparticles, mixed into the felt to enhance both how well the microbes stick and the efficiency of that electron transfer. This builds on foundational work, like studies that first detailed how bacteria can directly interact with electrodes, and more recent work optimizing conditions for harvesting electrons from these specific hydrogen-eating microbes. So these microbes are actively and continuously generating the current. It's a biochemical dance of energy conversion.
Fungi in a battery. That's genuinely wild. I mean, my first thought is decomposition forests, not power sources. How do they contribute to generating electricity? That feels totally counterintuitive. What's the secret?
This is truly one of the most innovative and, maybe mind-bending aspects of the NLB. This fungal scaffold layer is where you cultivate specific electroactive fungi. They mention species like Trametes versicolor or Neurospora crassa. These are grown on a custom 3D printed carbon cellulose matrix.
3D print.
Yeah, which acts as both their foundational growth substrate and an initial conductive pathway. 3D printing lets you design precise, intricate architectures to maximize surface area for the fungi and conductivity, while the cellulose makes it biodegradable. Now, these fungi play a crucial dual role. First, that 3D printed matrix itself forms a biodegradable electrode base, giving structure and some conductivity. But here's the breakthrough part. The mycelium, that vast, intricate thread-like network of the fungus, often hidden underground.
The main body of the fungus, right?
Exactly. It actually acts as a living conductive circuit. It's literally a natural growing wire network that conducts electrons.
Get out. Living wire.
Living wires. Imagine roots growing through soil, but these roots are actively conducting electricity, connecting different parts of the battery. The mycelium secretes enzymes, and during its metabolism, it can facilitate electron transfer, maybe similar to the microbes, or the fungal structures themselves can become conductive, forming this living interconnected grid.
Okay, but what makes that better than a normal wire?
Here's the critical difference. Unlike a static copper wire that, if cut or damaged, is just broken, this mycelial network has the inherent biological capacity to grow, adapt, and potentially self-repair.
Whoa.
If one part of the fungal network gets damaged, the fungus might be able to grow around it or regenerate new connections. That offers an unprecedented level of resilience and longevity in a power source.
That's incredible.
And to boost this conductivity further, the proposal suggests embedding materials like graphene oxide or carbon nanotubes right into that carbon cellulose scaffold. These nanomaterials have incredibly high surface conductivity and are great at electron transfer, improving the interaction with the growing fungal network. This builds on earlier work showing these materials can work well in biohybrid systems. So you're not just relying on static materials, you're harnessing the inherent growth, self-healing, and conductivity of fungi, making them active, integral parts of the electrical pathway.
Every electrical circuit, no matter how ingenious, needs to be completed for electricity to actually flow right. We've got the geochemical core making hydrogen fuel, the microbes acting as tiny electron factories, and the fungi as these amazing, living, self-healing wires. What's at the other end of this intricate system? What completes the circuit and lets us harness the power? Is there anything unique there too?
You're absolutely right. Completing the circuit is essential. That's handled by layer D, the cathode interface. This layer functions as an O-reducing cathode. This is the crucial point where electrons, having traveled through the external circuit, maybe powered your sensor, are accepted back into the system. That completes the flow.
Okay, so it uses oxygen, like many batteries.
Yes, in a typical battery, the cathode is where reduction happens, consuming electrons and a reactant, in this case, oxygen. Standard materials might be something like platinum mesh, which is very efficient, or other alternative cathode materials. But here's another remarkable innovation tying into the living aspect. The design includes an optional lichen or moss layer on top of this cathode.
Moss on the battery. Why?
It's not just for looks, definitely not. This living layer can provide natural photosynthetic oxygenation. So as the lichen or moss performs photosynthesis using ambient light, it produces oxygen. This oxygen is then used right there by the cathode to accept electrons.
So it makes its own oxygen for the reaction.
Potentially, yes. It helps regulate and ensure a steady, on-demand oxygen supply for the cathode reaction, helping complete the circuit efficiently. It's biologically generated oxygen.
That's clever. Any other benefits?
It could also help stabilize humidity within the battery, preventing the living components inside from drying out, and maybe offer some thermal regulation. So it's creating a self-regulating oxygen source and microclimate for the system, tying into that theme of using living systems for internal regulation and long-term sustainability. It's a beautifully integrated biological feedback loop.
Okay, that's pretty neat. A self-oxygenating battery.
Of course, ensuring the conditions are right for the moss or lichen to thrive consistently is a challenge, but the concept is very elegant.
So all these fascinating layers are working together, generating electrons, guiding them through living wires. But how do we actually capture the electrical output? How do we make it usable for our everyday devices? And how is the whole thing put together? How is it contained and managed in a practical way?
Right, good questions. Once the energy is generated, it needs to be harvested effectively and made practical. The electrical energy is directed through a load that's the device you want to power, like an LED, a sensor, a microcontroller, or it can be stored briefly in a capacitor to smooth out power fluctuations. Now, since these biological processes generate relatively low voltage, typically less than a volt per unit, you need to condition it for modern electronics. So an oscillator and a DC-DC converter are integrated into the external circuitry. The oscillator helps stabilize the signal, and the DC-DC converter steps up the voltage to a usable level, maybe 3.3V or 5V, ensuring the output is consistent and clean.
Standard electronics, basically, to make the biopower usable.
Exactly. Standard components bridging the gap. And for the whole system to be truly sustainable and practical, it's housed within a fully compostable biopolymer shell. This enclosure isn't just a simple box, it's designed to be functional. It incorporates moisture retention features, maybe using hydrogels or specific biopolymers to keep the living parts hydrated. It also has carefully designed aeration zones for necessary gas exchange, supporting the microbes and fungi.
Okay, and you mentioned modularity earlier.
Yes, crucially, the NLB is designed as modular units. You can easily link these individual units together in series or parallel, just like standard batteries.
Series for more voltage, parallel for more current.
Exactly. Series increases voltage for devices needing more push. Parallel increases amperage for higher power demands or longer run times. This allows for significant scalability and versatility. There's even an optional control and monitoring layer mentioned. This could include bioimpedance sensors, measuring the electrical properties of the living layers, or microbial activity sensors.
So you can check its health.
Precisely, providing real-time performance data on the battery's health, power output, potential issues, all without needing to open it up. It's conceived as a complete, integrated, adaptable, and inherently sustainable package designed for autonomy.
This is an incredibly detailed and frankly ambitious research proposal. It's not just an idea, it's a tangible pathway. What are the concrete, measurable, expected outcomes they're aiming for with this research? And looking bigger picture, if this natural living battery actually becomes a reality, moves beyond the lab, what are the broader implications for us?
The proposal does set very clear, tangible targets, which shows they're focused on practical results. Firstly, they aim to develop functional prototypes capable of producing more than 0.5 volts per unit. That's a key benchmark. And crucially, demonstrating the ability to stack these units for higher power outputs, proving scalability from the start. Secondly, a core objective is to rigorously demonstrate the viability of those biorenewable living electrodes, proving that the conductive parts can literally grow, repair, and renew themselves. That's a huge departure from current tech.
Yeah, the self-healing aspect.
Definitely. They also plan to establish benchmarked electrical profiles under various environmental conditions. That's critical for understanding how it would perform in the real world, deserts, forests, changing temperatures. That data is vital for engineering and any future commercialization. Ultimately, they intend to publish their results in leading scientific journals, bioenergy, materials science, ecological engineering, ensuring transparency and peer review. And remarkably, they even anticipate an open source release of their design.
Open source, wow.
Yeah, that's a powerful commitment. It means anyone, anywhere, could potentially replicate, build upon, and innovate with their work. That could foster rapid global innovation and accessibility.
So what does this all mean for us, for you listening? If we connect this to the bigger picture, what could this technology truly enable? And on a practical note, that timeline and budget you mentioned, they seem surprisingly lean for something this groundbreaking. That's almost as intriguing as the battery itself.
It really does raise fascinating possibilities for genuinely autonomous off-grid power solutions that are environmentally benign, from creation right through to degradation. Imagine those remote sensors monitoring endangered species, powered for years by the Earth itself. Or think about those educational tools allowing students to literally grow electricity, fostering a real connection to science and nature.
It's a different way of thinking about power.
It really is. It's not just an incremental improvement. It feels like a fundamental paradigm shift in how we conceive of technology's relationship with the environment. That concept of self-renewal and growth potential using living materials is perhaps the most profound implication. We're talking about a power source that doesn't deplete like a consumable product, but regenerates itself like an ecosystem. It flips our current model of consumption and waste towards regeneration and integration.
And the timeline and budget.
You're right to flag that. The proposal suggests final documentation and open source release within just 9 months of starting. That's incredibly ambitious for something this complex.
It really is.
It suggests a very focused, maybe agile development effort, perhaps leveraging existing research and readily available biological materials. And the estimated budget of around $6,000 for materials and strains is remarkably low. If successful, that low cost could make this tech highly accessible, potentially democratizing power generation, especially in underserved regions.
That combination, low cost, sustainable open source, could be truly transformative.
It could. However, we should also acknowledge the significant challenges, right? While the concept is brilliant, scaling up living systems for consistent power isn't trivial. Maintaining optimal conditions for those diverse microbes and fungi, ensuring long-term stability, managing contamination risks, these are critical engineering hurdles.
Real-world reliability.
Exactly. Power output consistency in fluctuating environments, the durability of the biodegradable shell, that all needs extensive testing and refinement. But the low cost and open source angle suggests maybe a collaborative, iterative development model could work well here, tackling these ambitious bio-integrated challenges together. It fundamentally challenges our current view of technology, moving from inert, consumable devices to integrated, dynamic living systems that are part of the natural world, not separate from it.
We've taken a deep dive today into the natural living battery, a truly innovative concept that brilliantly bridges ancient geochemistry, microscopic life, and these intricate fungal networks to create a self-renewing, biodegradable power source. It's a vision that moves beyond simply generating power to actively partnering with natural systems, designing technology that feels like it truly belongs in a post-carbon age where waste is minimized and regeneration is key.
Yeah, the aha moment here for me is that this isn't just about finding another, maybe slightly greener way to make electricity. It's about reimagining power production itself as an ecological partnership. Not just extraction from finite resources, but collaboration. It points towards a future where our technology could be as integrated, sustainable, and regenerative as the natural world it serves, rather than being a constant drain and leaving waste behind. It's a profound shift in mindset.
So for you, our curious listener, here's a final provocative thought to mull over. If our energy sources could truly be designed to be fully biodegradable and self-renewing, drawing power from the subtle, unseen biological and chemical processes happening all around us every single day, how might that fundamentally reshape our relationship with technology and the environment? What unexpected places might this living power source pop up next, maybe far beyond simple sensors and microelectronics? And how would that truly change the world we inhabit, transforming landscapes and lives alike?